All right, so now that you've had a chance to give this a go, let's talk through how you might logic out a way to determine what's going on. Okay, so I find it easiest to start with velocity because this is a velocity versus time graph. So here's my graph showing velocity on the y-axis there and time on the x-axis there. So I'm going to go step by step. And for the first section, the velocity starts right here and it goes to right here for those first 4 seconds. And I notice it's the same all the way across. It is between 6 and 4, so that would be 5, and then 5, 5, 5, 5. So the velocity during that section is 5 meters per second. I just read it straight off the graph. Then for the next section right here, it starts at time 4, and it's 5 meters per second, right? So I got 5 meters per second right there. And then it goes down, and at 9, it hits the x-axis, so that's 0 meters per second. So the velocity for this next section is slowing from 5 meters per second to 0 meters per second, right? So it's coming to a stop, right? It's going from 5 down to 0. Then I look at the next one from 9 to 19. It starts down at 0 and it goes up to that point there at 19, which is 10 meters per second. So my velocity for that section is speeding up from 0 meters per second to 10 meters per second during that time period. And then finally, the last section is the red section from 19 to 22 seconds. And I notice that it is staying the same. Here it's 10, 10, 10, 10. So all of them are 10 meters per second. So the velocity during that time period would be 10 meters per second. Okay, so now I feel pretty good about my velocities. The next part to figure out would be my acceleration. And for acceleration, I could think about the equation for acceleration. So I remember that acceleration is equal to the change of velocity over the change of time. So in this case, my velocity in the first section from 0 to 4 seconds, velocity starts at 5 and ends at 5. So how much did the velocity change during that time period? It went from 5 to 5. It changed not at all, right? So I went from 5 to 5, that's 0 change. And so my acceleration is going to be 0 meters per second squared. 0 meters per second per second. So there is no acceleration during that time period because the velocity is constant. So I could add in here, the velocity is constant at 5 meters per second, and same deal down for 10, it is constant at 10 meters per second. Okay, so acceleration is 0 meters per second squared there. And since I just looked at it, I also notice it's 10, 10, 10, 10 for that last section. So that's constant too. So that means no acceleration. The acceleration is going to be 0 meters per second squared there as well. Now there are 2 areas where my velocity does change. In here, from 4 to 9 seconds, it goes from 5 down to 0. So my final velocity would be 0. So if I were doing the equation, acceleration is equal to the change of velocity over the change of time. It went from 5 down to 0, so 0 minus 5 meters per second. Over the time change, it went from 9 seconds minus 4 seconds. So 0 minus 5 is negative 5 meters per second over 5 seconds. It declined by 5 meters per second over 5 seconds. 5 divided by 5 gives me negative 1 meter per second squared. So my value here would be -1 meter per second squared for my acceleration. Now for my next one, it's speeding up from 0 to 10 during this blue section, and that happens from 9 to 19 seconds. So from 9 to 19 is 10 seconds, and it goes up by 10 meters per second. So I could do my same change of velocity over change of time. It goes up by 10 meters per second over the course of 10 seconds, giving me 1 meter per second squared. So my acceleration there is 1 meter per second squared. Now, if I look at these values, I also notice that if I compare them to the graph, that's the same as the slope. So in here, the acceleration is equal to the slope of the velocity graph, right? When the slope was 0, I had 0 acceleration. When the slope was -1 during the yellow section right here, then my slope was -1. And when my slope was +1 in the blue section, my slope was +1 meter per second squared. All right. Now, the last set that we have to do is where is it actually located, right? What's the position for those pieces? So my position is starting at 0. I'm going to assume it starts at 0. And then in this first section, it goes 5 meters per second for 4 seconds. So I could use my equation, right? One equation I could use is that velocity is equal to distance over time. And I'm solving for distance, that's the position. So I'd multiply time by both sides to eliminate that one. And then I get distance equals velocity times time. Okay, so I have distance equals velocity times time. Well, my velocity was 5 meters per second. The change of time was 4 seconds. This one should be a change of time. So distance equals 5 meters per second times 4 seconds for a total of 20 meters. And it started at 0, so it went from 0 to 20 meters in position, right, during that 0 to 4 time scale. 0 to 20 meters. Now, the next piece is I'm going from 4 to 9. So one way that I could conceptualize this is I just did velocity times time. Well, the velocity is the y value, that much. The time is the x value, which is that much, 0 to 4. And then if I multiplied those together, what I really did was I took the area of that square, right? I took the area under the graph, the area under the curve for that section. So for the next one, from 4 to 9 seconds, I could do the same thing. I could take the area underneath that curve for that section, and that would tell me how much additional distance I would move. I could also say that this is like taking the average velocity, 5 to 0. The average would be 2.5. So it'd be like right there. And doing that, which would be the same space. Okay, so if I take the area there, that is 5 meters per second times 5 seconds. So it's 5 meters per second times 5 seconds, but it's also times 1/2 because it's a triangle. So it's always changing. So the average velocity would be half of 5, 2.5 meters per second, which gives me a total of 12.5 meters is how far I traveled. Since I was already at 20 meters, that would take me from 20 meters to 32.5 meters, right? That's my new position. 20 plus 12.5 is 32.5. All right, now I can do the same thing for the next set, the position from 9 to 19. So from 9 to 19, now I'm taking the area under the graph of that triangle. That is 9 to 19 is 10 seconds. And the height there is 10 meters per second. So 10 times 10, but then divided by 2 because it's a triangle. So half the area. 10 meters per second times 10 seconds times 1/2 gives me 50 meters is my change of distance. Now 50 plus my 32.5, I'm going to go from 32.5 meters to 50 plus 32.5 is 82.5 meters. Okay, so during that time period, I'm going 32.5 to 82.5. And then finally, from 19 to 22 seconds, I am going to take a look at that section. So this one, it's a rectangle. It's 10 high. It's 3 long. So I could say I'm taking the area under the curve right there. Or I could just note that this is, let's see, distance equals velocity times time, which is equal to 10 meters per second times 3 seconds for a total of 30 meters. And that's my change of distance. So I'm going from 82.5, 82.5 meters to add 30, 112.5 meters. So at 19 to 22 seconds, I'm going 82.5 to 112.5 meters. All right, so now I have a pretty good description for each of those sections. So during the first 4 seconds, the car is moving forwards from 0 to 20 meters at a constant velocity of 5 meters per second with no acceleration. Then for the next 5 seconds, from 4 to 9 seconds, the car is moving from 20 to 32.5 meters. It's slowing down from 5 meters per second to 0 meters per second with a constant acceleration of -1 meters per second squared. The car comes to a stop at 9 seconds at 0 meters per second, because that's 0 velocity. Then it starts speeding up from 0 meters per second to 10 meters per second over the course of the next 10 seconds. While it's doing that, it has a positive acceleration of 1 meters per second squared, and it moves from 32.5 meters to 82.5 meters in position. Finally, in the last 3 seconds, it has a constant velocity of 10 meters per second with no acceleration, moving it 30 meters forward from 82.5 meters to 112.5 meters. All right, and just like that, I have my completed motion of a toy car. I have included all necessary calculations. I have thoroughly explained the motion in terms of position, velocity, and acceleration. Great. Good work, us.